Hello, 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 welcome. Hopefully everyone can see me all right. Hello, those of you that have already said hi. Hi, Evie. Hi, Yanis. Lovely to have you. Hi, Madine. Hello, Hevra. Or Hevia, sorry. Can't read my small screen very well. Lovely to have you here. Welcome to anybody else. Please feel free to say hello in the chat. Hi, Kitty. Hi, Shania. Lovely to have you. And Koshani, great to have you as well. Welcome. Welcome back if you're somebody who's been before. I think there's a couple of names I recognise. Hi, Maya as well. Oh, and hey, Edward. Lovely to have you on this one too. Hello, Kinsey. Nice to have you. Hi, Tashita. Hello, Eggball as well. Oh, we've got loads of people. Hi, Jen. So I definitely recognise some of these names as people who have been to previous YouTube classes. But if you're a new student to our classes, then welcome. Lovely to have you here. Please feel free to, if you haven't already, download our slides. So the link should be in the description for you to have a look at. If you haven't already, download those because you can keep them for yourself for notes, for revision, maybe in a couple of weeks. You want to go back over everything again. Please feel free to do that. Also, don't forget to have a look back through all of our old YouTube classes. There may be some web classes that you weren't at, especially if you're a new student to us, then there may be some web classes you haven't seen before. So please feel free to go back and go over those as well. Lovely bit of revision for you. Nice, Sophia, welcome. Hi, Israth. Hello, Mr. AB. How are you doing? Hi, Catherine. How is everybody? Hi, Akil. Lovely to have you as well. Welcome. We'll give it another half a minute and then we'll get started. So, oh, hello, Evelina. Lovely name. Great to have you here. So we'll get started in a couple of seconds. So dynamic equilibrium is an AS content. We are only, I'm just double checking. I believe we're only looking at the AS content. Yeah, we are only looking at the AS content. So year 12 or first year A-level content here. I am doing another one, I know. Exactly. Those of you who have got exams coming up, you just have to push through for another couple of months and it's done. And although lots of exams, you know, if you go to university or perhaps a college course, you may do other exams. Personally, I felt my A-levels were the most stressful. So, you know, you may be different to me, but I think lots of people say that A-levels are one of the hardest times in your life when it comes to exams because you're doing perhaps 3, maybe 4 A-levels. You've got all of this knowledge to know about, you know, so it can be very stressful. So hopefully this will, you know, these revision sessions will hopefully help. And yeah, once you're done, you're done. Is this WJEC? So there's a lot of content overlapped, but we haven't specified this stuff for the WJEC exam board. Okay, so this will be useful for Edexcel because Edexcel, AQA and OCR are the 3 main exam boards that we make sure we cover. Unfortunately, we don't look specifically at WGAC, so you guys will have to have a look at that yourself. But there's, like I say, so much useful content in here, and there's huge overlap between all of the exam boards when it comes to A-level chemistry. So I'm sure there'll be stuff that you can use here. Yeah, got to get your A stars if you can. No, this will not cover KP for Israth. We're not going to go through KP, not in this web class anyway. Chemistry is hard. That's why. Chemistry is very hard. Oh, so great question about the seminar booklet. So I'm going to come on to that now. So let's get started and then I can answer that question in a second. Hi, Mahik. Lovely to have you. So I'm the lead chemistry teacher at SnapRevise. I've been teaching A-level chemistry for the last 7 years and tutoring and general science as well. I have a PGCE in science, but I specialise in chemistry because it's my favourite. And yeah, I love it. I love chemistry. I love how we can explain everything with, well, not everything, but most things we can explain with chemistry, which I think is amazing. Hi, Messiah. Lovely to have you here as well. Okay, so just to come to that question that we had earlier about the seminar booklet. So you may have seen us advertising this in our web classes before Easter. So we had some crash courses over Easter, which went through the entirety of the A-level chemistry syllabus. So we also did it in biology, physics and maths. If you're interested, the recordings, for the sessions are still available. If you want to head on to the SnapRevise website, you can find access to the recordings. You will get the seminar booklet posted to you. You can also email the tutor helper, what's it called? There's an email address that is dedicated to answering your questions if you have any issues. So please feel free to head over onto the SnapRevise website and check that out. So you can still buy them separately if you're interested. There's also package deals as well. So you can have a look at the package deals if you are somebody who's doing multiple subjects, or you want to do AS and A2, etc. So we did AS and A2 on different days. So if you are just an AS student, just want that, you can just buy one of them. If you would like to do both, you can do both. And we do have package deals for 4 or more sessions if that would be useful. Good. Yeah, maybe not. Perhaps not. Okay, lovely. So let's get started. So for this session, this session is being recorded and it will go on to our YouTube channel later on once it's been uploaded. So this web class that we're doing live now is being recorded and will be uploaded along with the rest of our back catalogue of these web classes. So our objectives, we are going to understand, hopefully, the concept of reversible reactions and equilibrium and why they come about. We're going to look at understanding Le Chatelier's principle. Apologies if I pronounced that wrong, but that's how I've learned to pronounce it. Also known as the equilibrium law. And we're going to apply Le Chatelier's principle to different environmental changes. We're not going to look at equilibrium constants though. Okay, so those of you that are part of the 3 main exam boards, we've copied and pasted the sections from your specifications into here. So this is AQA, this is OCR, and this is Edexcel. If you've downloaded the PowerPoints, you should have access to these. It's just at the beginning of the PowerPoint. I will say, and I always stress this because I think it's not said enough, the specification is such a useful resource, especially for A-level students, because there's so much content that you're expected to know. The specifications are basically a checklist of everything that you need to know in your specification. So you can go through with highlighters and pens and markers and everything. And you can say to yourself, do I know, for example, with Edexcel, do I know that many reactions are readily reversible and that they can reach a state of dynamic equilibrium in which I and II occur? Do I know that? Yes, tick. No, highlight it. Or is there a definition you need to know? Do you need to know about a mechanism? Do you need to know about a process? You can use these literally as a checklist if you need to work out what you do and don't know or what you need to revise for your exams. So go and download those from your exam board websites if you haven't already, because like I say, I think they are so useful and very underused. Okay. It doesn't like it when I turn my screen over. There we go. It just has a minor panic. I'm back. So what do we already know then? Can you give me some, yeah, sorry, I did disappear. Hopefully I'm back. Let me know if I'm not back. I should be back by now. Let me know if anyone still can't see me, or if you can't hear me, that would also be useful. I'm back. Thank you. Thank you guys. Well done. That's very useful when you're so responsive. Thank you. Okay, so give me some definitions. I don't mind which definitions you give me, but I want to see some definitions. So what's a closed system? What do we need in order for something to be a closed system? What is the system? When we talk about a system, what are we talking about? Versus when we're talking about surroundings, what are we talking about when we talk about surroundings? And then also endothermic and exothermic, what are they? And how do we know the difference? So go for it. Give me all the definitions that you think you know. Lovely. So a closed system is where no energy. Oh, I'm in red. Didn't mean to be in red. I meant to be in blue. I think blue is a bit nicer. Means no energy or matter is exchanged. So a closed system is when no energy or matter is exchanged, or we can say transferred to or from the surroundings. So a closed system is when we can have no energy or matter in or out of a system. So no energy or matter is exchanged or transferred to or from the surroundings. My handwriting is a little bit scrappy. If you can't read something and you're not sure what I've put, please let me know. Lovely. Really nice, guys. Some fabulous answers. So that's brilliant. Well done. What about our system then? What is the system and what is the surroundings? Hello, hello, welcome. If you've only just joined us, welcome. Lovely to have you here. Yeah, so lots of you looking at defining your endothermic and exothermic. So let's just do that now. N-E-N for enter. So energy enters the system is the way that I remember it. So endothermic is an overall heat transfer, heat energy transfer from the surroundings, entering the system into the system. So from the surroundings to the system. Well done if you got that right. Well, fabulous. And then exo, so that's endo, exo, energy exits. So there is a heat transfer from the system to the surroundings. Energy exits the system. Really well done if you got that right. Lovely. Yeah, well done those of you that have worked out what the difference is between the system and the surrounding. Yes, the system is the reaction that is happening. It is the matter that you are studying, the matter that is interesting to you. So our system is the matter, which is usually the chemical reaction, so the reactants and the products that you are studying. And the surroundings is everything else. Everything else. Well done, those of you that said that. It is any other matter or everything else. Any other matter, everything else, which is difficult because actually the surroundings can often be the solvent that you're doing the reaction in. And that can make things a little bit complicated for us sometimes. So the system is the matter you're studying. Oops, I can't spell studying. Studying. And the surroundings is anything else, everything else around it. Really nice, those of you that said that, lots of you did. Fabulous. Okay. Let's look at why have we worked all this? Why have we checked we know this? Let's have a look. What is dynamic equilibrium? So, an irreversible reaction. This is what we normally talk about when we discuss chemical reactions at Key Stage 3, a little bit more at GCSE, although we start to think about reversible reactions at GCSE. So an irreversible reaction is what? And how does it differ from a reversible reaction? Good. One arrow, one direction. Not the band, unfortunately, but an irreversible reaction is normally what we just consider to be a forwards reaction, a single direction of reaction. So for example, A plus B goes to make C plus D. Good. One direction, forward only. Reaction can't go the other way. Yeah, brilliant. Well done, everybody. Joseph, yes, this is recorded. It will be on our YouTube channel if you want to come back and watch it at a later date. And please feel free to go and have a look at all the other ones we've got as well, because we have got other pre-recorded ones on there too, and in other subjects, physics, chemistry, maths, and biology. So please do go and investigate those. Yep, lovely. Look, so this is OCR, EdXL, and AQA. Brilliant, lovely. It looks like everyone's got that. So the reaction goes forwards only. Looks like lots of you have got that. Anyway, what about a reversible reaction? How do we tell that something's a reversible reaction? How does it differ? Yeah, lovely. Brilliant. It's that weird, yeah, double. Now it's odd because we often, lots of people call it a double-headed arrow, even though it's not double-headed. It's two arrows. It's a double arrow. Half an arrow goes one way, half an arrow goes the other way. Brilliant. And it can go both forwards and backwards. So we've got A plus B goes to make C plus D, but also C plus D can go to make A plus B. So really, really nice. If you got that, that's absolutely fabulous. And so we can describe it as the reaction, reaction can go both forwards or in the forwards direction and in the backwards direction. Lovely. Fabulous. I was just about to ask, has anybody got an example of one? So the Haber process is a reversible reaction. Something else that you may remember, especially if you are an A2 chemist, is you may be aware that if we have the formation of an ester, so carboxylic acid plus an alcohol, this is a lovely what's the word? Reversible reaction that you can study. So we've got condensation, the removal of a small molecule, i.e. water, going in the forwards direction, or hydrolysis, the addition of water across a bond in the backwards direction. And our product, well, let's make that R1, is our ester bond, R2, and water. Yeah, so this is just an example. You don't have to know this specifically as a reversible reaction, but just an example of a reversible reaction is esterification, or the creation of an ester, for example, from a carboxylic acid and an alcohol. So you don't have to know that at A level. Okay, let's have a look then at what, yeah, there's a couple of other examples that people have given as well, which is great. Well done. Let's have a look at why we're interested then. So dynamic equilibrium, we need to be able to give the two reasons, and this is the reason I didn't read it out on the specification earlier. We have two reasons, or two, two phrases that we need to be able to recall about a closed system at dynamic equilibrium. You need to be able to recall in an exam. What are those two things? How do you know, or what is the evidence that a system is in dynamic equilibrium? What are we looking for? What happens or doesn't happen when a system is in dynamic equilibrium? Anybody know? Lovely. Brilliant. Well done. Everyone seems to have got this one perfect, which is fabulous. So something along the lines of, you don't have to be exact, but something along the lines of the rate of the forwards reaction the rate of the backwards reaction. Now, it doesn't have to be identical, but it is useful to use the term the same or equal in this first point. The rates of the forwards and backwards reaction are the same. They are equal. Things are being converted into reactants at the same rate that they're being converted into products. Okay, so the rate is equal. Perfect. Has anybody thought of the second one? Oh, somebody has. Oh, and yeah, at least two people, a couple of people have, sorry. So the second one, well done those of you that said it. I think I saw a couple of people, Tammy, Alyssa, and somebody else earlier. Pogba, exactly. So the other thing is that the concentration of our reactants and products are constant. Yeah, we have to, in this case, we have to use that term, constant. So the concentration of the reactants and products remains constant. And in this case, you have to, I think, it is You're less likely to lose a mark, let's say, if you memorize the word constant for this second one. The concentrations of the reactants and products remain constant. They remain constant. They're not the same. They might not be the same as each other, but they are constant. They do not change. So you can say they don't change. You would get the mark for that. You can't say they're equal because they're not equal. And in terms of confusion, I also wouldn't say they're the same in case you make a mistake and say they stay, in case you say they are the same instead of they stay the same. So I would forget that and just remember the word constant for this second bullet point. Yeah, pressure, only in gaseous molecules, but yeah, that's it. We can think about pressure and concentration as being very similar to each other. If you're talking that, you can use them interchangeably as long as your units are the same. But that's a very good point. If you say that the concentration isn't changed, that's a very good question. No, I don't think you would lose the mark. The thing I'm just warning against is lots of people say that they're equal, or they say they are the same, and they are not the same, but they remain the same. So as long as what you say is very clearly saying that they remain constant over a period of time, you'll get the mark. Just be really careful when with word use, basically. Lovely. Yeah, good. Okay. Very good. Well done. Okay. What about this picture then, or this diagram? This is showing us a system in equilibrium. Which color, hopefully you can see the colors in this case, which color shows us the reactants? Which color shows us the reactants? So we've got a little reaction up here. We've got NO2. Oops, should be 2 NO2. Apologies, there's a mistake there. 2 NO2 goes to make N2O4. Which is showing the reactant in this case? Looks like most of us are saying blue. Good, and it is blue. How do we know it's blue? How do we know it's blue? Really nice. Well done, those of you that said it's because the concentration is decreasing. So we're assuming, therefore, that blue is showing a reactant because the concentration is decreasing, and because red is starting off at 0. So if red is starting off at 0, that must be a product of which we've got none to begin with. We're looking at it over time, across time. So we start with none of our product. We start with some of our reactant, and over time, our reactant decreases and the concentration of our product increases. Really nice. Well done, those of you that got that. Okay, the other thing I'm going to ask is what aspect of this graph tells me that, no, sorry, I'll change my question. At what point on this graph have I reached dynamic equilibrium? At what point on this graph have I reached dynamic equilibrium? Oh, so we've got 2 different suggestions going on here, guys. We've got the green line or where they cross. So, oh yeah, okay. Well done, those of you that have noticed. It's at the green line. And again, this is a common error for students, as we've just illustrated. That point there is simply, on this graph, simply the point at which they have the same concentration. That's not the point at which they are at dynamic equilibrium, because, as we've already looked, at dynamic equilibrium, the rate of the reactions must be equal. So they must have the same gradient on this graph, because the gradient, concentration over time, is the rate. So they must have the same gradient at that point, and their concentrations must not change. They must remain constant. And so that is after the green line. That is when the graph becomes constant, or the lines become constant, the concentrations become constant. So this is when we have reached dynamic equilibrium. Is anyone not happy with that? So at the green line is when we've reached dynamic equilibrium, not before, at that green line. Good. And exactly, AB, exactly as we were saying before, the concentration doesn't have to be the same. It can, and they can be really, really mean and give you a graph where dynamic equilibrium is reached at the same point at which the equilibrium is the same. The concentration is the same, but it's so unlikely. It's very, very unlikely that you're going to get a reaction where you happen to make dynamic equilibrium occur at the point at which the concentrations are identical. So much, much more likely that you're going to get a graph that looks something like this, and we're looking for the point at which the lines level off. The PowerPoint for this lesson is in the chat, what's it called, the description underneath the box. There are other sessions like this, and we have been doing free sessions on YouTube for years. So please feel free to go back and have a look in our archives, as it were, to find other sessions. This one, obviously, we do Sunday sessions every Sunday in maths, physics, chemistry, and biology, and we rotate around the subjects. So keep an eye on our schedule and work out if you want to come to any future sessions. That would be amazing. Okay, lovely. Let's keep going then. So Le Chatelier's principle, again, apologies if I say it wrong, but Le Chatelier's principle, also known as the equilibrium law. So you may, one of the examples, and I'm just going to double check which one it is. I think it's Edexcel. So Edexcel doesn't name it in the specification as Le Chatelier's principle, but you will have talked about it, and you may have called it the equilibrium law, or you may have just discussed what happens when you make a change at dynamic equilibrium. So it's still the same. It doesn't matter that you don't have the name for it. Doesn't matter. The principle is still exactly the same, but that's what I'm talking about. And this is covered in all three exam boards. So it tells us how the equilibrium concentrations will react to changes in the environment. So we're just going to talk about concentrations for now. So what is Le Chatelier's principle? What is the equilibrium law? Does anybody think they know? Ah, hello, Bella. You knew exactly what I was going to ask then, didn't you? Brilliant. Well done. Anybody agree or anybody disagree? Brilliant, well done. There are some fabulous answers here. Oh, yeah, loads. I think those, yeah, good. Yeah, brilliant, really, really nice. So Le Chatelier's principle, the equilibrium law, says that a system at equilibrium will move or adjust to counteract a change or a stress that has been placed on it, exactly as you guys have said, which is brilliant. So when a system at equilibrium is subjected to a stress or change, the equilibrium, and you can say external stress or change, the equilibrium or system will adjust to address or correct, oops, can't spell, address or correct the change or stress. You can also say to minimize the effect, to minimize the effect of the change. Now, you don't have to be able to recall this word for word. You may notice, as we've had lots of brilliant examples, that you can say variations on a theme, and it's not, you know, that's, you're still likely to get the mark. They're not too worried about exact wording here, but just make sure you're giving the, you're making it very clear what it is that you're talking about and that you are covering all bases. So when a system at equilibrium is subjected to a stress or change, or an external change, an external pressure, an external stress, the equilibrium position will adjust or will change to address or correct that stress, or to counteract the change is a nice way of putting it. Yeah, brilliant. Yeah, that is the same sort of thing. It's a negative feedback, and like that whole principle. It's very, very similar. You're adjusting to minimize a change. Yeah, exactly right. So in terms of describing our equilibrium positions, if you've got a reactant going to make a product, this probably should be actually reversible arrows here. So you've got reactants going to make products, products going to make reactants. If the equilibrium sits quite far over to the left, that means, and I'm using a dot to describe it, that will mean that the equilibrium is shifted to the left. That means that at that point, the rate of the forwards reaction is more, no, come on brain, higher than the rate of the backwards reaction. No, other way around. Rate of the backwards reaction is higher than the rate of the forwards reaction. My brain turned off then apparently. So at this point, our equilibrium position oh gosh, I can't spell. Equilibrium position is shifted to the left. Now, there's quite a few different things you can say here. Oh, sorry. Oh gosh, what's happening? Ah, my screen started flipping forwards for no apparent reason. That was exciting. I don't know why I did that. Silly technology. The equilibrium position is shifted to the left, or you can say in the backwards direction, or you can say towards the reactants. Now, all of them mean the same thing. And as long as they haven't asked you for something specific, like the position of equilibrium, talking about it in terms of the forwards and backwards direction or something in the question, you can use all three of those terms to describe the same thing. So you may see lots of it written in lots of different ways in exam papers. Yeah, sorry about that, guys. That was a bit. So reactants, and if our equilibrium is towards the product this time, then again, we can describe it as being sorry, my pen being silly again, equilibrium position is shifted. And again, we can say any of these three phrases. We can say it's shifted to the right. We can say it's shifted in the forwards direction. And we can say, oh, that's supposed to say towards. Or we can say, uh-oh. Sorry, I think my laptop is really having a fun moment. Maybe someone's got access to my mouse or something. No, they probably haven't. Or what did I say? Equilibrium position is shifted to the right or in the forwards direction or towards the products. Lovely. Yes, we haven't, we're going to come on to that in a second. We're going to come on to that in a second. Yeah, don't worry. We haven't talked about counteracting any changes or anything yet. This is just how we describe equilibrium positions. Yeah, sorry, we haven't looked at any stresses yet. This is just talking about the position of equilibrium, how we describe the position of equilibrium. Okay, how confident is everyone feeling? I'm running a little bit behind time, so I'm probably not going to do this exam question. How's everyone feeling? Give me a 1 or a straightforward or a smiley face if you're feeling, yeah, pretty confident about what we've just done. A 2 or a if you're feeling, yeah, it's okay, I guess. I might want to go over it again maybe. Or 3, oh my gosh, no, this is brand new to me, or I hate it, or if that's how you're feeling. Fair enough. Good. Lovely. So this is as much for me to see how you guys are doing as it is for you guys to take the opportunity to evaluate your own learning. So how are you feeling about it? Is this something you maybe want to go over, or are you actually feeling okay about it and can probably go on to do exam questions on it? It does totally doesn't matter. Yeah, however you're feeling is however you're feeling. Lovely. We're not going to have time to do this exam question, I'm afraid, but just to allow you to do it yourself and then mark it, it says give 2 features of a reaction at equilibrium. We just need to give those 2 features we mentioned back on our page on dynamic equilibrium. Concentrations are the same. No, concentrations remain constant. I made my own mistake there. Concentrations remain constant, or the rates are the same for that exam question. So feel free to have a go at that one. But we're going to move on to have a look at Le Chatelier's principle. Okay, so now we're going to talk about how our position of equilibrium shifts and why. So for any reactants or product in solution, so we're talking about solutions, so we can think in concentrations, the position of the equilibrium will be affected by changes in concentration. So if we increase A, I'm going to do these in 2 different colors so I can leave my scribbles up. So if we increase the concentration of A, hopefully everyone's happy, square brackets means a concentration of. So an increase in the concentration of A, what's going to happen to the position of equilibrium when we increase the concentration of A? Which way is the equilibrium going to shift? Lovely, brilliant. Well done, everyone who said it is going to shift to the right. To counteract the change, it's going to want to use up the A that we've added, which actually means you're going to end up with more C and D produced. So as we increase the concentration A, it causes the position of equilibrium to shift to the right. And we would end up with more C and D to counteract that change. So we would get more C and D produced in our system. Really nice. Good. Very, very well done if you're happy with that one. If I change color, I'm going to go to red so we can do the other one in red. What happens then if we have an increase in C? What if we increase the amount or the concentration of C? What happens to the equilibrium position then? We increase the concentration of C. Lovely. I like the emoji with that as well. Good. It's going to shift. I'm going to do it underneath just so they don't clash. It's going to shift the position of equilibrium to the left. We're going to try to use up that extra C. We're going to use up the extra C to get more A and B. So an increase in C causes the position of equilibrium immediately after the change to shift to the left to counteract that change, producing more of our A and B, although perhaps more, yeah, producing more of our A and B, more of our reactants. Brilliant, yeah, lovely, totally agree. Well done, everybody, fabulous. Okay, so that's with concentrations. So we're used to, when we talk about our, what's it called? Collision theory. When we do collision theory, we talk about the effect of concentration on rate, we talk about the effect of temperature, and we talk about the effect of pressure. So we're going to look at all of those now as well, because they're all useful. So in an equilibrium reaction, if the forward reaction is exothermic, the backwards reaction is endothermic and vice versa. This is the same principle if you have covered it, if you're thinking about Hess's law or Born-Haber cycles, if you've covered it yet, if you're in A2. The same principle here. If the forward reaction is exothermic, it gives out energy. The same energy, that same amount of energy will be required to be taken in for the backwards reaction. The energy change between the reactions and products must be identical. So it either needs to give out the same amount of energy or take in the same amount of energy. And we can be told which direction they are. So if the forward reaction is exothermic, then the backwards reaction must be endothermic and vice versa. So it looks like people have already guessed what it is I'm going to ask. Delta H, my enthalpy, is less than 0. Enthalpy is less than 0. So that means my enthalpy is negative. And therefore, is this exothermic or endothermic? If more of solid B is added, does the position of equilibrium change? Good question. No, I don't think it would. You wouldn't be asked that at A level anyway, which is good. But no, I don't think it would, because you're not increasing the concentration or increasing the surface area. So you would increase the rate of the reaction, but I don't believe it would change the position of equilibrium. Good. This is exothermic. Well done, those of you who said that. The forward reaction is exothermic. We normally give this on the right-hand side to show that the forwards reaction is exothermic. Okay, therefore, if the forward reaction is exothermic, the forward reaction is giving off heat energy. If we increase the temperature, which way is the position of equilibrium going to move? So if we increase the temperature in an exothermic reaction, which way is the position of equilibrium going to move? Lovely, Ikra, that was a really nice explanation. Fabulous. It's going to move in the endothermic direction, to the left, towards the reactions, in the backwards direction. Those are all four of those phrases are all legitimate answers to the question. So really, so increasing temperature. Oh, I've done it again. I've pressed the button. Sorry, let's just sort that out. Come back. Red. Shifts the position of equilibrium towards the left, toward, no, go back. Me and this laptop are going to have an argument in a minute. Towards the reactants, left, or in the endothermic, or backwards direction. You can say all of them correct. You can say towards the reactants, you can say towards the left, you can say in the endothermic direction, or you can say in the backwards direction. All of those. Chemistry is great. Okie dokie. Lovely. What about our other one then? So here, our enthalpy is greater than 0. That means our enthalpy change must be change is positive. Then it must be, hopefully everyone's happy. The forwards reaction is endothermic. So what happens when we increase the temperature in an endothermic reaction? What happens if we increase the temperature in an endothermic direction? Where is the position of equilibrium going to shift? Nice, Ikra, well done. Fabulous, those of you who said it will shift the position of equilibrium in the endothermic direction again. Equilibrium. So in this case, because our endothermic direction is the forwards direction, the products, it will in the endothermic or forwards direction. Really nice, well done. To the right in the endothermic direction. Brilliant, well done, fabulous. Let's whiz on because I'm aware we're slightly running out of time. What about with pressure then? We've looked at concentration, we've looked at temperature, now we're looking at pressure. For any gaseous reactants or products, the position of equilibrium will be affected by changes in pressure. So if we change the amounts of gaseous reactants or products, we can affect the position of equilibrium as well. So if we increase the pressure here, which direction is our equilibrium going to shift? An increase in pressure will shift the equilibrium good. So if we increase the pressure, we're going to shift the equilibrium towards the I'm going to say side, even though that sounds a bit odd, towards the side with fewer gas molecules, which in this case is to the right. They like to sometimes trip you up. We're only interested in the gas molecules. If you're increasing pressure, we're only interested in gas molecules because the pressure of liquids and solids barely changes. So we're only interested in the side with a fewer or less gas molecules. Really nice, well done. Does it depend on the moles? Yes, 100%. It depends on the moles. So we've got 1 mole of gas on the right, 2 moles of gas on the left. So it's going to move towards the right-hand side in this case. Ah, fair enough. Cool, good. To be fair, our state symbols are quite big compared to the size of the chemicals. You're probably used to seeing them a little bit smaller, so that might have been more confused you. Okay, decrease in pressure then. What if we decrease the pressure? Which way is it going to move? What if we decrease the pressure? A decrease in pressure will shift the equilibrium which way? Equilibrium. Good, to the left. Now, I find it easier to work it out when you increase pressure rather than when you decrease pressure, and then I have to kind of think about it in reverse. But exactly right. Shifts the equilibrium to the left, as in towards the reactants, because that has more or a greater number of gas molecules. No, not necessarily, because if you consider that liquids and solids have a very stable and consistent volume, when you increase or decrease pressure, the only thing that's going to be changing the volume that you're going to be changing the volume of or the pressure of is the gaseous substances. So you can basically ignore liquid and solid substances in this case. It's a good thought, a good thing to be aware of, but it doesn't matter. Okie dokie. I've got no idea, Zara. Does it have to be with entropy by any chance? Oh, this session, we're going to finish in about 5 minutes. Mr. AB, we're going to finish in about 5 minutes. Does it have to be with entropy? So, Tommy, that's a really great question, and that's something we're not actually covering in this session, but it is a fabulous question. Entropy can be considered separately to this. So, you wouldn't be asked to consider the entropy change alongside thinking about positions of equilibrium. Because this is a system at dynamic equilibrium, it's a good thing to think about, but in the same with enthalpy as well, you wouldn't be asked to consider the change in enthalpy or any issues associated with enthalpy or entropy when you're considering the position of equilibrium. I guess because it's a dynamic equilibrium, you've already overcome the barriers of entropy, if there are any, or enthalpy. So we can kind of ignore them, I guess. But it's a very good question. Okie dokie. Right, final thing then that we're going to cover. What is the effect of catalysts on the position of equilibrium? What is the effect of catalysts on this, on the position of equilibrium? How do catalysts affect the position of equilibrium? Really good. Well done. Nobody fell into our trap. Catalysts do not affect, even with an A, affect the position of equilibrium. What do they affect? What do they affect? They provide an alternative route with a lower activation energy. Absolutely. Good. They affect the rate. They just affect the rate of reaction. And so if you add a catalyst to a dynamic equilibrium, to a reaction, the dynamic equilibrium will be reached faster because the forwards and backwards reactions will occur faster. So it just affects the rate of reaction in both directions equally. So equilibrium is reached faster, but the position is not affected. Lovely. Okay. Fabulous. I apologize. I'm sure there were some questions in there that I missed. There's lots of you today and you've been doing brilliantly. So I'm really sorry if I didn't manage to answer your question. We've looked at understanding the concept of reversible reactions in equilibrium. We've looked at understanding Le Chatelier's principle, and we've looked at applying Le Chatelier's principle to different environmental changes. I'm afraid we didn't manage to get through our exam questions, so apologies for that, but please feel free to have a go at them yourself. And if you have any major issues, hopefully a little bit of Googling or reading back through the content that we've covered should help. If anybody has any quick questions, then please feel free to ask them whilst I just talk through our final little bit here. So if you have any questions, just pop them in the chat. But whilst, if you are somebody who's been coming to these YouTube sessions for a while, we do a YouTube session every Sunday. It will be in either maths, physics, chemistry, or biology. And they're free for everyone and as interactive as you want them to be. We, over Easter, did some A-level exam crash courses, and the recordings are available for you to purchase if you would like to have a go. It's like a mini crash course on A-level chemistry. It is based on the advanced information that was given out by exam boards. It covers all three of the main exam boards, AQA, OCR, and EdXL. We talk through some exam technique in the first hour of each session. So there's a day on AS chemistry, there's a day on A2 chemistry, and there's the same for physics, maths, and biology. The first hour we spend doing exam content, and then we go through the trickier aspects of the advanced content for the course, answering a range of exam questions and talking through the content. We have got these amazing seminar booklets, which if you are interested in purchasing our booklet, it has all of the content in it and a load of exam questions and a mock paper for you to have a go at as well. They are amazing resources, and that will get posted to you. So if you're interested and you fancy having a go at that, if you go to https://course.snapprovised.co.uk/recording-2022, you can have a go. If you fancy purchasing it, then please go and investigate. There are discounts for, and the link has just been sent to you in the chat. There are discounts if you want to purchase 4 or more So if you're doing multiple A levels and you perhaps want to purchase 4 or more, you can get discounts. I believe you can get 1 for free if you purchase 4. So please go and have a look. If you've got any questions, well, hopefully somebody did have a question, which I think I've ignored. Hopefully I've answered most people's questions, but hopefully I'll see you again at one of these. Thank you so much for being so attentive. You've been brilliant. And yeah, really well done. Good luck in your exams. Hopefully see you at a future web class. Or if you fancy joining us on SnapRevise, the reason I have to rush off is I'm about to go teach a couple of A-level chemistry classes on the website. So if you're interested, go and check those out as well. So have a lovely evening. Good luck with your exams. Apologies if I didn't manage to get to your questions. And I will see you very soon. Thank you, guys. Well done.